So we'll continue with chapter 5 review, and chapter 5 starts with writing chemical equations and balancing chemical equations to satisfy the law of conservation of mass that says you should not create or destroy matter, which means atoms, and you should retrieve the number of atoms you had to start with. You should retrieve them on the product side, right? Remember how we call the formulas written on the left of the arrow, we call them reactant. The arrow symbolizes the change, and then on the right side we have the product. And so these equations that are not balanced yet, we call them skeletal equations, because they are just showing the formulas of the reactant and product, but they are not balanced. So we'll continue with the reaction D, or equation D. Let's resume recording. Oh, I see. I need to put this on speakers. Okay. So we said we had one aluminum on the left, one on the right, one hydrogen on the left, two on the right, and chlorine we have one on the left and three on the right. So we are ready to balance, and we can start with hydrogen because aluminum is already balanced for now. So we have two hydrogens on the right and one on the left. So we will want to make it 2 also on the left, because that's easy by multiplying by 2 here. And I will put this in a different color so we really see. So this, oops, oh, sorry. So we want to make 2 hydrogens on the left, and for this we will put a coefficient of 2 in front of HCl, because that's the molecule that has the hydrogen. So you want to place the coefficient in front of the molecule that has the hydrogen. So that balances hydrogen, but you see that the 2 here will also change the number of chlorine, because the 2 also will change the number of chlorine, because chlorine is part of this formula. So that means here we need to recount the number of chlorine we have, and so it's not 1 anymore. It's going to be 2 chlorines now. So we have 2 chlorines also on the left, due to the fact that we, placed that coefficient in front of HCl. So that means we need to balance chlorine now, and we have 2 on the left and 3 on the right. So let's make make it 6, because when you have 2 and 3, there is no easy way to use 2 or 3. You have to take the common multiple of 2 and 3, and so it's going to be 6 on both sides. So that means you will want to multiply by 2 on the right side. Let me change that to green. And that means we will want to multiply by 3 on the left side, so that it's times 2. It's going to be 6 also. So let's place the coefficient of 2 on the right in front of, so that's for chlorine. So we will have to do it in front of AlCl3, because that's the molecule that has the chlorine. So we will place the 2 there. So we have 2 times 3, the subscript 3 here, will make 6 chlorine. And that will change also the number of aluminum. You can see that. We can do this right away and say aluminum now, it's not 1 anymore, but it's 2. So on the right side, if we go back to chlorine here, so we have 2 times 3, 6 chlorine on the right. We want 6 chlorine on the left, and we have 2 at this time because the coefficient in front of HCl is 2. So, but we want to make it 3. So in fact, that 2 will be removed, and we will make it 6 directly. So it's going to be directly a 6 instead of 2 times 3 here. Let's make it 6. So now we have 6 chlorine on the left, 2 times 3, 6 chlorine on the right. Aluminum, we still have 1 on the left, and now we have 2 on the right because we placed that coefficient 2 in front of AlCl3. And so hydrogen, there is, we need to recount here. There is 6 hydrogens on the right, so let's, I guess I have to erase that and say that we will make it 6. So we have 6 hydrogens on the left, and on the right it's still 2. So we need to balance hydrogen on the right by making it 6 everywhere. So that means we will want to make it times 3 here. And let's choose another color, times 3. So we'll make it 3 here. So if we recount everything, well, I see right away that aluminum is not balanced, so let's balance aluminum. So you see how it's a play of you put down some coefficients, but then you need to change them. So here aluminum, we have 2 aluminum on the right and only 1 on the left. So let's make it 2 also on the left by placing a 2. Let's make it times 2 here, times 2. So let's recount, and I guess to make it easier to see, let's recount. So we have hydrogen, chlorine, and aluminum. Let me do one thing so that it's not so spread out. Okay, so let's recount aluminum. Right now we have 2 aluminum on the left and 2 aluminum on the right. So that's balanced. Hydrogen, we have 6 hydrogen on the left and 3 times 2, 6 hydrogen on the right. So that's balanced. And then chlorine, we have 6 chlorine from HCl, 6 chlorine on the left, and 2 times 3, 6 also on the right. So it looks like now everything is balanced. Sorry, this one was a bit tricky with the interruptions, but let's make it nicely with this one now. Do you have questions on the previous one? Okay, so let's do equation E. Oops. Oh. I only wanted a space here. Okay. So let's count. I'll just copy that so that I have my. Oh boy. No, not a 2 like that. Okay. So we need to count sodium and oxygen. There's only 2 elements in that skeletal equation. So let's count sodium. Sodium on the right, right now we have 1. On the left we have 2. Oxygen on the left we have 2 oxygen from the subscript here. And on the right we have 1. So they both need to be balanced. So let's start with sodium. We have 2 sodium on the right, only 1 on the left. So we want to multiply by 2 on the left so that it will be 2 on both sides. And so to make it 2 sodium on the left, we will place a coefficient of 2 in front of Na, because that's what we are trying to balance here. So the 2 will go in front of Na. And that would balance sodium. We need to balance oxygen. We have 2 on the left, 1 on the right. So ideally, we want to make it 2 on the right by placing a coefficient of 2 in front of Na2O. But you can see right away here, by doing this, we have 2 oxygen on the left, 2 oxygen on the right, but we change the number of sodium. And it's not 2 sodium on the right anymore, because the two molecules of Na2O means that you will need to count 2 times 2 for sodium. Sorry. So that's 4 sodium now. So 2 times 2 is 4 sodium on the right. And we have 2 sodium on the left because we placed that coefficient earlier. So it looks like we'll need to cancel that and change it to 4, right? To make it 4 on the left as well. So this gets let's make it 4 instead. So the 2 here will be changed into a 4, and I will make it green so we realize it's a new thing here. Okay, so we need to recount to make sure. Let's recount, and we have sodium first. So sodium, we have 4 sodium on the left. And 2 times 2, 4 sodium on the right. And then oxygen. So we have 2 oxygen on the left and 2 oxygen on the right. So it looks like it's balanced. So this one was not too hard, even though we have to go back and forth, you know, and change the coefficient. that we place at first. But that's what balancing is about. You need to adjust until you have the final answer. So you always want to recount in the end with the coefficient you have decided to keep and make sure this is balanced. So let's do this one. And so this one is going to be a tricky example. So it's important we follow this one carefully. So we'll count our atoms, and let's do this. So we'll count carbons. So you want to do them in that order. In the order they appear in the chemical equation. Carbon, hydrogen, and then oxygen. It is important for a compound that contain carbon and hydrogen, and when there is oxygen also in the chemical equation, that you do them in this order. Carbon, hydrogen, oxygen. And you want to balance them in that order. So let's count the number of carbons on both sides. So carbon on the left, there is 4 from the C4H10. And carbon on the right, there is only 1 from the CO2. Hydrogen on the left, there is 10 from the C4H10. And then there is 2 from H2O on the right side. Oxygen, there is 2 on the left in the molecule of oxygen. And on the right, you have 2 from the carbon dioxide plus 1 from the molecule of water, right? So 2 here from the carbon dioxide and 1 from water. So that means 3. So I told you want to balance them in the order that they are written here. So carbon first, hydrogen, oxygen. So let's start with carbon. So we have 4 carbons on the left, only 1 on the right. And so let's make it 4 on both sides by multiplying by 4 on the right. And so that coefficient of 4 will have to go in front of CO2 because that's the molecule that has the carbon. So you will place a coefficient of 4 in front of CO2 to have 4 carbons. Now let's do hydrogen. We have 10 hydrogen on the left. We want 10 hydrogen on the right because times 2, that's going to be feasible. So let's multiply by 5 because 2 times 5 is going to be 10 also on the right. And that coefficient of 5 will have to go in front of water because water is the molecule that has the hydrogens. So we have a coefficient of 5 in front of water now. And you can see that those coefficients of 4 and 5, they change the number of oxygen in CO2 and then change the number of oxygen in water as well. So that means this first count here is not useful. We need to redo it. So it's now 4 times 2. Oops, 4 times 2. From CO2, the coefficient times the subscript, plus 5 times 1 in water, 5 times 1 oxygen per water molecule. And so that's a total of, 5 plus 4 and 4, 8, that's 13, right? So that means we have 13 oxygen on the right now instead of 3. So, and on the left we still have 2 from the molecule of oxygen. So whatever you will do to the molecule of oxygen here, O2, whatever you put in front, the coefficient you put in front, will only apply to oxygen. So that means, after all, it's not too difficult to balance because you can then make it any coefficient you want so that you have the proper number of oxygen. So because we have 13 on the right, let's make it 13 on the left. Because you see that this molecule of C4H10, you don't want to have to put a coefficient in front if you can help it. So let's just make it balanced on oxygen using whatever we need to make it 13 on both sides. But what you put in front of O2 will be multiplied by 2. So we have to make it 13 divided by 2. And 13 divided by 2 is 6.5, right? It's 6.5. 6 and 6 is 12 plus half is 13. So by making a coefficient of 6.5 on the left side in front of O2 here, because it's going to be multiplied by the 2 subscript, we'll have also 13 oxygen on the left. So that's how you would balance it. The problem is, you may have seen that already in the lectures of chapter 5, is that the coefficients, they have to be whole numbers. They have to be integers, and you cannot leave it like this. So even though it's convenient because it balances everything, you cannot leave it like that. And so to solve this problem, what we do is we multiply all the coefficients by the number that will be necessary to make this 6.5 a whole number. And here we can see that 6.5, to be a whole number, we need to multiply by 2. So then you will multiply everything by 2. And for this, we will show how we multiply everything by 2 by putting an accolade here. Another, forgot how it's called, but maybe it's accolade. By multiplying all the coefficients by 2, we will be able to have a whole number for everything. So then we will need to rewrite everything. So let me do some copy paste here. So if you multiply the coefficient in front of C4H10 by 2, it's going to become a 2 because there was nothing there before. So that's a 2 now. 6.5 here multiplied by 2 will become 13. So that's going to be 13 oxygen. The 4 here multiplied by 2, that's going to become 8. And the 5 multiplied by 2 is becoming a 10. And so that's the way we want now to have our coefficient. So we need to make sure, and let's recount. That is blue. So let's recount the carbon. And then the hydrogen, and then the oxygen. So carbon, on the left we have 2 times 4. You need to multiply the coefficient by the subscript. So 2 times 4 is 8. On the right, there is 8 carbon from 8 CO2, because there is 1 carbon per CO2, so 8 on the right side. Hydrogen is only in C4H10, and there is 10 hydrogens times 2 molecules, so that's going to be 20 hydrogens. Sorry for the noise. 10 hydrogens on the left, and 10 times the subscript 2 on the right side, right? You do the coefficient 10 times the subscript 2. And then oxygen. Oxygen, there is only oxygen in O2 here, and it's a coefficient of 13 times 2. 13 times 2 is 26. So 26 on the left. On the right, so we have from two sources. We have 8 times 2 from the CO2, 8 times 2. The coefficient times the subscript, plus 10 times 1, right? 1 oxygen per molecule. So I can do that. And so let's add that together. So 2 times 8 is 16, plus 10, that's 26. So we do have 26 oxygen on the right, just like on the left. So it looks like everything is balanced. And so then this shows how your equation is balanced. And so this kind of thing where you have to multiply all the coefficients by 2, or you know, depending on the coefficient that is not a whole number. If it's a number that is you know, over 3 or you know 0.333, you would multiply everything by 3. If your coefficient here would be a fraction over 4 or a 0.25, then you would multiply all the coefficients by 4. So you adapt the number you multiply all the coefficients by to, you know, such that you want the coefficient that is not a whole number to be a whole number. So this happens a lot when you have this kind of combustion reaction, typically. And whenever you have an odd number of oxygen, it's always the oxygen who creates this kind of problem. And it's when it's an odd number, typically, not always, because sometimes you have oxygen in the molecule there, and that helps you get a odd number. But often it's when you have an odd number, and then you need to balance the oxygen on the left side. So that I have only one example of that, you know, in this review. So are you all right with the balancing? So please tell me if you have questions on balancing, because we'll move on to... Yes, you have a question? Or was it yes, you're all right? Okay. So we can go over the different types of reactions. So the chapter 5 then next goes to explaining the different types of reactions, and if you have not seen them yet, it's going to be hard. Let me say that combination, the key to recognize a combination reaction is that you have an X plus a Y, and they will make, let me make an arrow. Let me insert something if possible. No, there's no arrows there. Okay. So a combination reaction has the form of X plus Y, 2 reactants or more, give only one product, and here would be XY. You put them together, you create a bigger molecule. So that's combination. You have only one product. Decomposition is the reverse. You have A and B together, and you're making A plus B. You're breaking down, you're breaking down the big molecule into smaller pieces. So that's a decomposition. You are breaking down a big molecule and breaking it into 2 or more, you know, product. A single replacement, and I guess I should just insert. Single replacement looks like this. So you have an element so a single element, which means just one type of symbol, plus a compound, and let's make it a BC. They will give a new compound, so let's make it AC, plus a new element, B. So a single replacement looks like this. You have an element plus a compound that will give a new compound. So, you know, atoms rearrange, they change partners, if you will. And you're making a new compound, and now it's a new element that is by itself, right? B is an element. So that's a single replacement. A double replacement, it's quite similar, except that you start with two compounds. It's AB plus XY that give a new compound, so two new compounds, I should say. And so let's see, it's going to be AY plus XB. Yeah, the reason why I put them in that order is because typically this kind of double replacement reaction happens with ionic compound, and the A would be the positive ion, the B would be the anion, the negative ion, and so same with the X and Y. The X would be the positive ion, the Y would be the negative ion, and so, you know, A, which is positive, will have to go with Y, which is negative. So that's why the new compound is AY, and then the X, which is positive, will go with B, which is negative, and make a new compound. Sorry. It's ringing everywhere. So, stop. Okay. So a combustion reaction is a very different way of classifying chemical reactions, because it's typically a compound made of carbon, and so let me add again something like that. So C, X, H, Y, and sometimes there is oxygen there. I mean, well, okay. These are subscripts, right? The X is a subscript. I guess I should remove it from here. The Y is also a subscript. Should be an H there. And then the OZ will be also subscript here for Z. Okay, so it's that. A compound made of carbon and hydrogen, and sometimes oxygen or not, will react with oxygen from the air. Oxygen from the air is O2. Sorry. So the oxygen, when you find it in the air, it's the molecule O2. It's an element because it's made of only one type of atom, right? We call it a diatomic molecule because it's more than one atom, but it's two atoms of the same kind, so it's classified as an element. And then we produce from that. This is not part of the, sorry. And we produce CO2, and that's a gas, plus H2O, water. Also in the form of a gas, because, you know, typically you're burning something when you do a combustion reaction. So combustion is synonymous to burning, and the general form of a combustion reaction is like that. And here you really can specify the, the physical state. It's oxygen gas, you produce carbon dioxide gas, and steam, water as a vapor. The CCXHYOZ can be solid, liquid, or gas. But a combustion reaction looks like this. You are producing carbon dioxide and water when you're burning a compound that contains carbon and hydrogen, and to burn it you need oxygen from the air. This is something I really want you to remember out of this course, because we use combustion reactions a lot to get energy, because these reactions are very exothermic, we call that, which means they release a lot of heat to the surrounding. And so, for example, you're burning methane, natural gas, or gasoline, or kerosene, wood, charcoal, and wax, all kinds of things that are made of carbon and hydrogen. And we are burning by using oxygen from the air and releasing carbon dioxide and water into the atmosphere. And we use those products and burn them to get energy, right? The reason why we do this is to get energy, from natural gas to cook or warm our houses, gasoline to drive our cars, and kerosene to fly in planes. So all of these are used to get the energy from them, all the fossil fuels, right? So now that you know the different types of reactions that exist, I want you to classify reactions B through F that we saw earlier. So let's do F, because we have it under our eyes here. So what kind of chemical reaction, what type of reaction is the reaction F? This one here. So you need to tell me by chat, or you can, speak up. There's not that many of you, so you can unmute. So tell me, what do you think this reaction is? No one has an idea? Are you still hearing me, right? So you should see that this equation is made of compound that contains carbon and hydrogen, and reacts with oxygen from the air to produce carbon dioxide and water. Yes, it is combustion. That's a typical example. Let's make that purple so we see it. Yes, that's a combustion reaction. Let's go through, it's going to be hard to see the different types. And so, let's see, it's not. Okay, so reaction E says 4Na plus O2 gives 2Na2O. What do you think this is? So 4Na plus oxygen gives 2NaO. Is it a combination, decomposition, single replacement, or double replacement? So 2Na plus O2 gives 2Na2O. We said for combustion is very specific about what are, the product, what they are. It's carbon dioxide and water. Yeah. Or maybe there was a typo there. Yes, it's a combination, because the key to recognize a combination is that you have one product only. So this one is a combination. because you see only one product being made from 2 or more reactants. So that's the key to recognize combination. So let's look at D. 2Al plus 6HCl gives 2AlCl3 plus 3H2. So we have aluminum, and aluminum is a solid in this case, plus HCl, that's an aqueous solution, gives AlCl3 and H2. So, okay, there is a replacement there, but are you sure it's a double replacement? Because if you look, a double replacement starts with 2 compounds and is making 2 new compounds. A single replacement is starting with 1 element and a compound and making a different compound and element. So yes, this is a single replacement because we start with aluminum. Aluminum is an element, HCl is a compound, and we are making a different compound, AlCl3, and a different element, H2. H2 is an element, because even though there is a subscript here, it's more than one atom, it's only one kind of atom, hydrogen, and so it's still classified as an element, because, you know, it's only hydrogens. So single replacement. You start with an element and a compound and make a new element and a new compound. So let's look at this one. CaOH 2 times plus 2HNO3 gives 2 molecules of water and 1 of CaNO3 2 times. So maybe I can go back here, show you the different types. Is it a combination, a decomposition, a single replacement, a double replacement, or a combustion? So we start with CaOH 2 times plus HNO3. It's not a combustion because you're not burning with oxygen in the air and producing carbon dioxide and water. Yes, it's a double replacement because you start with a compound made of calcium and hydroxide ions. The OH is the hydroxide ion, so that's a compound. The HNO3 is another compound made of, that's an acid actually, made of the nitrate ion and the H plus ion. And yeah, because H, even though it's a nonmetal, it makes H plus ion, it's really different from other atoms. And so what happens is that calcium will exchange partner and will get rid of the OH minus and take on the nitrate, the NO3, right? You see now that calcium is with NO3. And you remember how we said that water needed to be seen as H-OH because water is basically made of H bonded to OH. And so the OH, they will bind with the H plus from the HNO3 and they will make H2O. So you have to see water as HOH, and then now the OH and the H plus are together, so they have exchanged partners. So let's write somewhere, let's see here. double replacement. So that's a double replacement. We started with two different kinds of compound and made two new compound. B, we can still do B. So 2Ni3 gives N2 plus 3I2. So let's go back to the list of types of reactions. It can be a combination, a decomposition, single replacement, double replacement, or combustion. And yes, here you see right away there is one reactant only, making, being broken down into N2 and I2. So that's what we call a decomposition, because you are breaking down one molecule into smaller pieces. So this is called a decomposition. And I prefer, well, we could do this one now that we know how water can be seen as a, no, I don't want to do this one. We'll stop with B. Okay. So that's for this third question. Okay. So yes, there are many ways of classifying reactions, and the first four names here: combination, decomposition, single replacement, and double replacement, are a way to tell how the atoms are rearranging. So you take into account the number of reactants and products, and you take into account if you start with elements or compound. So those four ways of classifying are similar. Combustion is really a different way of looking at it. And there is even other ways that are called acid-base reactions and precipitation reactions that you will see in your lab for, and that are not listed here. But that combustion, acid-base, and precipitation are different ways of looking at reactions. So if we focus, I really want to show that this one is kind of different. If we focus on the first four, so it's a classification that follow what happens to the atoms. And in a combination, so you see the word combining. So you're combining two or more reactants, and here I symbolize the reactant with the X and Y, and it doesn't have to be elements. My X and Y could be compound. It's really a general way of showing you have more than one reactant. And they combine together to make a bigger molecule. And so the XY here symbolize the fact that you put all the atoms together to make a bigger molecule. So combination really is, the key is that you have one product made from two or more reactants. Combination and decomposition are really opposite processes, because the decomposition, for the decomposition, you start with a compound that is fairly large, and you break it into pieces, so two or more products. So it's really the reverse process of a combination, because this time you are decomposing, which means breaking down into smaller pieces. And so to recognize a decomposition, you need to see that it's one reactant only, broken down into two or more products. So that's the key to recognize a decomposition. And then a single replacement. So here it matters that I have one letter or two letters together, because the A here symbolizes an element. So one element plus a compound will give yields. So one element plus a compound. The element here is symbolized by the symbol A. It's like an element, and remember how some elements are, diatomic molecules like H2, N2, O2, F2, Cl2, Br2, and I2. The 7, gases that are found as diatomic molecules. So made of one type of atom elements, plus a compound made of at least 2 different types of atoms, yields a new element. Well, I'll write compound because that's what is shown first. A new compound and a new element. Right? A is an element plus BC is a compound. They will yield a new compound, AC, and a new element, B. So B represents my element. AC is the new, let's just make it plus, right? So that's how you recognize a single replacement reaction. And then a double replacement reaction. Again, here it matters that I have AB, which is meant to represent one compound. So actually it's 2 compounds because 2 compounds, AB and XY, represent 2 compounds. They are made of at least 2 different kinds of atoms. They will exchange partners, which can be ions, or if it's ionic compound, they will exchange ions, and that's typically what happens. These double replacement are typically dealing with ionic compounds. They exchange partners to make 2 new compounds. Right, because AY is a new compound and XB is a new compound compared to AB and XY. I hope that makes sense. The combustion reaction, as I said, is really a different way of seeing things, because here we're very specific about what is produced and what reacts. So in a combustion reaction, it's a compound. Oops. It's a compound made of at least carbon and nitrogen. It can have also oxygen. Made of carbon and hydrogen. It will react, but I want to say burn because it's really what it is. It's burning. Whenever you are burning something, you are doing a combustion reaction. So a compound made of carbon and hydrogen will burn with oxygen from the air. So oxygen from the air, okay, I will write it like this, but from the air. So it's O2, right? The formula of oxygen that we breathe is O2, and it's a gas, O2 gas, because you don't see it, right? It's a colorless, odorless gas. We are not really aware of it until we lack oxygen, right? So we'll burn with oxygen from the air to produce carbon dioxide, and carbon dioxide is CO2 gas. It's always a gas at room temperature, right? CO2 is a gas at room temperature. And okay, I will write water, but it's water. Because you're burning, you have to really realize that water at those temperatures will be a gas. So H2O gas. And that's why, for example, when you are running a car, driving a car, and in there you're burning gasoline. So gasoline is what you input in your car. It takes the oxygen from the air, so that's why you need a good ventilation going into the engine, and it burns. So there is a spark, in the ignition chamber. There is a spark. The gasoline will burn with the oxygen, and you will produce carbon dioxide and water. And so, at the back of your car, you have the gas. I forgot how it's called, but gas pipe, and sometimes you see water dripping from there, right? When the car is not very warm, you see water dripping from the gas pipe in the back of the car, and that's because you're producing water, and it got cooled down enough to become liquid again, and so it drips from the gas pipe. But the carbon dioxide, it will always be in the form of a gas, because carbon dioxide rarely goes into the liquid state. We're able to make a dry ice with the carbon dioxide, and so dry ice looks like ice, but a bit more opaque and white. And out of the dry ice, you see the vapors of carbon dioxide escaping. So you go directly from a solid to a gas without going through a liquid phase. And the vapors are going downward. They are, heavy. They are more dense than air, so they flow downward. So it's nice to see. Anyway, I'm deviating here. A combustion will always have that form. You will always have oxygen, specifically oxygen as a reactant. It will burn with a compound made of carbon and nitrogen, and you will make carbon dioxide and water. So that's the different types. And I could add a precipitation reaction. And you've seen a lot of these during lab 2. During lab 2, you saw a lot of formation of precipitate. A precipitation reaction will be of this kind. It will be like a double replacement. It's really what it is. But you know that these are ions, so it's like I shouldn't do that because. But it's like oops. How to do this? Well, okay, what characterizes precipitation reaction is that there are solutions, aqueous solutions, and they're making a solid. So one of the compounds you make will be a solid, and the other will still be soluble in water and an aqueous solution. And so the key to recognize precipitation reaction is that you're making a solid here, right? And this solid here, so precipitations are, let me think. Sorry, I can't find my words. Precipitation reaction is when you are mixing two aqueous solutions and they form a solid called a precipitate. They form a solid, a precipitate. Right, and so the precipitate here is your S. You need the S. Those letters in parentheses represent the physical state of the compounds or elements, right? So to recognize a precipitation reaction, you need to have the formation of a solid from aqueous solution. You need to have aqueous solutions to start with. But if if you look at a precipitation reaction, really what it is, it's a double replacement reaction where you have exchange of ions because they are happening between ionic compound. They exchange ions, and when they exchange ions, one of the new compound is a solid. It doesn't dissolve in water, and it makes a solid. And so it's those powder you saw forming in solutions. And then there is the acid-base reactions, which are also double replacement reactions. They look like that as well. But okay, let me make it like this. Acid plus base. An acid plus a base will make H2O and a salt. I guess I don't need to put that in big letters here. Base, acid. That's subscript here. Okay, but they are based on the double replacement reactions. The acid, okay, because, and I'm really going too deep in there, but that's going to be helpful for lab 4 anyway. So because the acid contains H plus ions, and the base contains, it's really a general form of acid-base reactions. They are not all like that, but a lot of them are. Contains the hydroxide ion. You recognize how OH minus is the hydroxide ion, a polyatomic ion. And the base contains OH minus. And together, H plus OH minus make water. Let me insert an arrow. H2O. Well, okay, that's again a subscript H. I guess I could have everything in there. H. Well, okay, I'll do that later on. So the H plus ions combined with the hydroxide ions to make water together. You see that, if you put them together, you have 2 H's and 1 oxygen, and that's the formula of water. So that's the general form of an acid-base reaction. An acid plus a base gives water plus a salt. We'll go into more detail in chapter 9 because that's the topic of chapter 9. But precipitation reaction and acid-base reactions are double replacement reactions. I guess I can say that. Double replacement reaction where an acid plus a base give, oh, it's too long. Yes, it's a pity it's cut there. Okay, so I'm sorry, I kind of extended way too much here, but that's things you will need to learn, and this will be useful for lab 4, which lab 4 is based on chapter 5, right? Don't be fooled by the number. Lab 4 is requiring the knowledge of chapter 5.